All right, let's get into it. Today, we're going to crack the code on a topic that pops up in pretty much every tech interview. And, let's be honest, can be a little intimidating. String questions. We're going to level up your entire approach.
So, you have to wonder, why do interviewers lean on these questions so heavily? I mean, we've all been there, right? You get a string problem and your brain just goes into overdrive. Is there a trick? What are they actually trying to figure out about you?
Okay, let's break this down. It's because strings are kind of the perfect test. In one neat little package, they can check your understanding of core data structures, algorithms, and just your general problem-solving mindset. It's about way more than just text.
To really start crushing these problems, we've got to go back to basics, level 1. And the first, most important mindset shift is to stop seeing a string as just a word. You need to see what it is underneath.
Because, at its absolute core, a string is just an array of characters. That's the big secret. Each letter has a position, an index, starting from 0, exactly like a regular array. And once that clicks for you, you suddenly have this huge library of array-based solutions at your fingertips. And this is where it gets powerful. Thinking this way immediately connects common puzzles to things you already know. For instance, need to check if a word is a palindrome? Boom, use the two-pointer technique. One at the beginning, one at the end, and just walk them inwards. Trying to see if two words are anagrams? Just sort the characters in both and check if they're the same. And counting characters? That's a classic job for a hash map.
Okay, so seeing strings as arrays, that's our foundation. But what happens when the problem gets bigger? When you're not just fiddling with one string, but you're trying to find a tiny string inside a massive one. For that, we're going to need a serious upgrade.
This is the absolute classic substring search problem. You've got a huge block of text, maybe millions of characters long, and a small pattern you need to find. This question, in some form, comes up all the time.
Now, this is where you can really show the difference between a good answer and a great one. The brute force way is obvious. You check every single spot the pattern could possibly start. It works, sure, but it's slow. We're talking O of n times m time. A much smarter way is to use an algorithm that pre-processes the pattern so you can make these huge logical leaps and skip massive chunks of the text. That gets you down to a much faster O of n plus m.
One of the most famous of these smart algorithms is Boyer-Moore, and it has this really cool kind of counterintuitive trick. It compares the pattern from right to left. Now, why on earth would it do that? Well, because when you get a mismatch, you learn something incredibly valuable from the character in the text. You can then use a lookup table to figure out the absolute maximum distance you can jump forward, often skipping tons of useless comparisons.
All right, now for the final level up. We've handled structure, we've handled searching. But what about problems that are all about prefixes? I'm talking about things like autocomplete or searching a dictionary. For these, we need a very special, very cool data structure. The Trie.
Just think about it for a second. You type BE into a search box, and it instantly suggests bear and bell. How does it do that? I mean, scanning the entire dictionary for every word that starts with B every single time you type a letter would be insanely slow. There's got to be a better way.
And there is. The answer is a trie, which you'll sometimes hear called a prefix tree. It's a tree where each path from the root down represents a prefix. Instead of storing entire words in each node, you just store characters. You know what? Let's just build one. It's way easier to see it in action.
So we always start with one empty root node. Now let's add the word bear. It's simple. We just create a path from the root, a node for B, which points to a node for E, then A, then R. That's it.
Now here comes the magic. Let's add the word bell. We start at the root, we follow B, then E. Hang on. We've already built this part of the path for bear. And that's the whole point. We reuse the existing B prefix and just branch off from the E node to add our L and L. Super efficient.
Let's add one more, bid. Again, we start at the root. We reuse the B node we already have, but this time, the next letter is I, so we create a new branch. See what's happening? All the words starting with B are neatly organized under one branch, and all the words starting with B are in a sub-branch. Finding every suggestion for an autocomplete is now just a matter of walking down the tree.
So we've covered a lot of ground here. We went from seeing strings as simple arrays to using smart search algorithms, all the way to building this custom data structure. Let's pull it all together into a toolkit you can actually use.
This right here.
This is your interview cheat sheet. The real key to acing these interviews isn't about memorizing 100 different solutions. It's about recognizing the type of problem you're facing. So, when you get a question, ask yourself, is this about reordering or structure? Go for array techniques. Is it about finding a needle in a haystack? Use a pattern matching algorithm. And if it's about autocomplete or prefixes, your answer is the trie.
And remember, this stuff isn't just some abstract puzzle for an interview. These concepts are the bedrock of so many things we use every day. From the search engine in your pocket to the labs that are literally sequencing DNA, these string algorithms are the invisible engines running in the background. They are fundamental tools for building the future. So the real question is, what are you going to build with them?